let's finish things. The next one or the last one is also like this but somewhat different. Exercise 7. Let R be a ring. Possibly non-commutative. It may or may not be commutative, in which if the product of two elements is 0, then that implies at least one of them is 0. If A and B are two elements in R, and again same condition, and A to the power m is equal to B to the power m for 2 relatively prime positive integers m and n, prove that A is equal to B. Okay, so the beginning is just like the previous exercise. If at least one of the two elements A or B is 0, then the result is trivial. Okay, the result is easily seen to be true if A or B is 0. So assume both A, B are non-zero. Right. Okay, now note one thing. Since we have positive integers n and m for which A to the power n is equal to B to the power n, so by the well ordering principle, there will be such a smallest positive integer. Either n or m itself is such a positive integer which has the smallest value for which these two powers are equal, or there is a smaller one. In any case, there will be a smallest positive integer d for which A to the power d is equal to B to the power d. So let d be the smallest positive integer such that A to the power d is equal to B to the power d. In fact, let C be is happening, let C be this element. Okay. Okay, now by the Euclidean algorithm, Euclidean algorithm is the one which gives us a quotient and a remainder when we divide an integer by a non-zero integer. So here we are dividing m by d, because d is positive, so we can do that. By the Euclidean algorithm, there exists non-negative integers q comma r such that m is equal to qd plus r. Okay, by the way, why r is non-negative, that we already know. That comes from the algorithm itself. Why is q non-negative? Because if q is negative, then we have a negative number here, because d is positive and r is positive, but since r is less than d, you cannot add r with this to make m, because m is also positive. So that's why q is non-negative. If you find it confusing, you try to convince yourself that the fact that d and m are both positive forces q to be non-negative, where r satisfies these inequalities. The remainder is smaller than the divisor. Okay. Now 0 is equal to a to the power m minus b to the power m. So in place of m we can write qd plus r minus plus r. So this is equal to, this can be written as a to the power p. Oh, they have taken p. Okay. So this becomes a to the power d whole to the power q times a to the power r minus b to the power d whole to the power q times b to the power r. So this is equal to, now what is a to the power d and b to the power d? C, and that c can be taken common out. So actually we have c to the power q common out. Inside we have this. Since okay, now look at this condition. Product of two non-zero elements has to be non-zero, because if product is 0, then at least one of them must be 0. So here the product is 0, so one of them must be 0. Since C is non-zero. Why is C non-zero? Because you see A and B are non-zero. So multiplying two non-zero elements cannot give us 0. So here we are multiplying A with itself d times. That gives us C. So C cannot be 0, and this condition is coming from here. Okay, so since C is non-zero, or we can write like this, since C to the power Q is non-zero, as C is non-zero, we have A to the power R minus B to the power R is equal to 0, or A to the power R is equal to B to the power R. Now note that R is a non-negative integer for which this is happening, but according to us D is the smallest positive integer for which this happens. So since R is less than D, R cannot be positive. So we write like this: the minimal nature of D forces us to conclude that R is equal to 0. Now if R is 0, that just means that D divides M. D divides M. Similarly, one can show that D divides N. By working with N in place of M, one can show that D divides N. So D is a common divisor of M and N, so it will divide their greatest common divisor. Thus, D divides the greatest common divisor of M and N, which is nothing but 1, because M and N are relatively prime. But D is a positive integer, so this implies D is equal to 1. But if D is 1, then from here itself we will get the fact that A is equal to B. Hence, A is equal to B. And this ends the solution and the set of exercises. But there is a problem. Do you spot some gap in this solution? What about this part? Is it justified that I can write like this? Because it seems here that I am using laws of exponent, but in which group? That question is there, right? It turns out that we can in fact apply laws of exponent provided all the integers that we have are non-negative in a ring, even if the ring is not a field. This fact I think I have not proved, but in a special exercise I have proved it somewhere. I will show you that this can be done in a ring also, provided all the integers are non-negative, so that these powers make sense. We don't have any negative integer. That's why we stressed the fact that we have non-negative integers. For this calculation to work, it is absolutely necessary for Q to be non-negative. If Q is negative, then this becomes meaningless. I mean, once you reach this, after that you cannot do anything. Okay, so with this I end this set of exercises and section 3.6 ends. Now we will go back to the second section of the first exercise, section 1.2, which involves functions, because someone wants that. After that is over, I will briefly go back to analysis, because I haven't gone to analysis for quite some time, and then we will again come back to ring theory. And in the course of doing these things, I may start group theory. So with this I end this video, If you are new here, please subscribe to my channel, A Mathematical Room. So this is me, Lucifer, signing off. Have a nice night.